This video aims at last minute revision on the chapter Semiconductors. It's a quick revision on important concepts and questions related to semiconductors. As per the CBSE syllabus, this chapter covers 7 marks out of 70, 10% for the CBSE board exams. This is the first video on semiconductors. This chapter relatively more theory oriented chapter with limited number of numericals. The types of numerical questions asked from this chapter are very easy to understand and apply. So if you take a good care of this chapter, 100%, 7 marks from this chapter can be scored for the board exams. The first concept is classification of materials based on energy band diagrams and the extension of that into different type of semiconductor categories. So all the energy band diagrams is discussed as a single topic here. The first broad classification is materials into conductors, insulators and semiconductors. Semiconductors are further classified into intrinsic and extrinsic semiconductors. Extrinsic is further subdivided into N-type extrinsic and P-type extrinsic semiconductors. We start with the first broad classification. For conductors, there are two types of energy band diagrams. Here, the conduction band and the valence band are separated by an energy gap, but the conduction band and valence band both are partially filled. The conduction band is partially filled. The valence band is partially empty. Normally the valence band will be completely filled, but here in this case the valence band is partially empty and the conduction band is only partially filled. So conduction is possible when electrons in the lower level moving up to the higher levels in conduction band or in the valence band. The lower level electrons in the valence band can move to the upper level because their levels are vacant here. Even the electrons in the conduction band can move in the higher levels. So this leads to the conduction. Even there is a small energy gap, since the conduction band is partially filled and the valence band is partially empty, conduction is possible due to movement of electrons from lower level to higher level. Now the second diagram for conductors, the conduction band and valence band overlap so that the energy gap is zero. So this is the base of the conduction band. This is the top of the valence band. So this region is the overlapping region. Arrow mark overlapping of conduction band supposed to be extended till here. This is the overlapping of conduction band with valence band. The energy gap is zero. So electrons can very easily make the material conductive. Generally, when conductors energy band diagram is asked, the second diagram is mostly preferred, the one with energy gap 0. If they ask two cases for conductors, then only you are supposed to draw the first diagram. That is what normally seen in the board marking scheme. The second diagram where conduction band is overlapping with valence band. If they ask very specifically for two different cases for conductors, then you have to draw the partially filled valence band conduction band and overlapping conduction band valence band, otherwise the second one. Now the second broad classification is after conductors it insulators. In insulators, the energy gap is more than 3 electron volt. So the conduction band and valence band separated by an energy gap which is greater than 3 electron volt. Normally the conduction band will be empty because this large energy gap normally not supplied by thermal energy. Any electron from valence band to excite to the conduction band, it must absorb energy at least equal to the energy gap. Normally heat energy cannot provide energies of this energy gap required for the excitation. So these materials, insulators, do not have any electrons in the conduction band. The valence band will be completely filled. So not possible to conduct. Now the third category under broad classification is semiconductors. For semiconductors, the energy gap will be less than 3 electron volt. So the upper level of valence band and the lower level of conduction band separated by energy gap less than 3 electron volt. Good examples for elemental semiconductors are silicon and germanium. Silicon have 1.1 electron volt which is less than 3 electron volt, and germanium have 0.7 electron volt which is again less than 3. So those two are elemental semiconductors. In those cases, the thermal energy, heat energy, can provide sufficient energy for the electron in valence band so that it can enter the conduction band. So easy to conduct with the help of thermal energy. This is the broad classification of materials into conductors, insulators and semiconductors. Then we are concentrating only on semiconductors category. The semiconductors are further subdivided into intrinsic and extrinsic semiconductors. Intrinsic semiconductors are pure semiconductors without any addition into the material, like pure silicon or germanium are examples for intrinsic semiconductors. If the intrinsic semiconductor is at 0 Kelvin, there are no thermal support, no heat energy available for the electrons in the valence band to excite to the conduction band. Since no support of external energy is available, the valence band will be completely filled, the conduction band will be empty, no electron will be able to enter the conduction band because there is no thermal energy supporting the thermal excitation. So the valence band will be completely filled, the conduction band will be completely empty. So an intrinsic semiconductor at 0 Kelvin acts as an insulator. Now the same intrinsic semiconductor is at room temperature greater than 0 Kelvin. As we discussed here, the energy available, heat energy available from surrounding, help the electrons to jump from, excite from valence band to conduction band. So if 4 electrons gain energy to jump to the conduction band, there will be 4 free electrons in the conduction band. Same time, there are vacancies of 4 electrons. They left the valence band and moved to the conduction band. These vacancies or absence of valence electrons, that is known as electron holes. So the free electrons and the holes both are equal in the case of an intrinsic semiconductor, pure semiconductor at temperature greater than 0 Kelvin. So Ne, the free electron concentration, is equal to the hole concentration NH. the product of Ne into NH. Both Ne and NH are intrinsic semiconductors. So both these can be classified as Ni. So Ne into NH equal to Ni into Ni, that will be Ni square. That is applicable to intrinsic and extrinsic semiconductors. It's coming in the next step. For an extrinsic semiconductor, we are doping the intrinsic semiconductor with external elements so that the conductivity of this intrinsic semiconductor can be enhanced. Here the conductivity of intrinsic semiconductor is very low and it depends upon temperature. Any change in temperature can show much variation in the conductivity. So we are adding external elements to increase the conductivity and reduce the temperature dependence on the conductivity. So in an n-type semiconductor, so these doped semiconductors are called extrinsic semiconductors or external elements. So in an n-type semiconductor, we are adding group 15 elements into an intrinsic semiconductor, which is normally group 14, silicon or germanium. So out of the 5 valence electrons of group 15, 4 electrons are used for forming covalent bonds with the neighboring for group 14 atoms. For example, if you are adding antimony or arsenic, which is group 15, into silicon structure, the silicon structure demand 4 bond, but the antimony arsenic have 5 valence electrons. So the 4 electrons in the valence band are used for bonding with neighboring for silicon or germanium atoms. The 5th electron, by absorbing energy, can become free. So this is the energy level of the donor atoms. The 5th electron is donated by the group 15 atom for conduction. So it's called donor atom. So this is the energy level of the group 15 atom. This is the conduction band of group 14. This is the valence band of group 14. When you are adding group 15 elements, their energy level is coming to be very close to the conduction band of silicon. The difference is only 0.01 electron volt. So with this amount of energy, 0.01 electron volt, the electrons from the group 15, the 5th electron, which is not involved in any bonding, can easily jump to the conduction band of silicon. Before an electron to move from valence band to conduction band of silicon or germanium, it needs 1.1 or 0.7 electron volt for germanium, 1.1 for silicon. But when you add a group 15 atom, its energy level is coming to be very close to the conduction band. It demands only very low energy, 0.01 electron volt for excitation. So along with this excitation, the thermal excitation from valence band to conduction band also will take place. But since this demand only very less energy, it will be more frequent. The one demanding 1.1 electron volt will be very rare. So here one hole, so that one electron is jumped to the conduction band by thermal excitation of group 14 atom. The rest all the electrons available here are from group 15 atoms. So except one electron which came from valence band to conduction band of group 14, the remaining all free electrons are donated by the group 15 atom, because it demands only very less energy for making the group, the 5th electron of the group 15 atom to be free. So here you can see large number of free electrons compared to holes. So Ne is greater than NH. Here also Ne into NH will be same as Ni square. Now the second type of extrinsic semiconductor is p-type semiconductor. In n-type semiconductor, we dope with group 15 into group 14. Here we are doping with group 13 atoms into group 14. So group 14 crystal structure demand 4 covalent bonds, but group 13 atoms only have 3 valence electrons. So when they are added into group 14, out of the 4 bonds, 3 bonds are completely filled. In the 4th bond, there will be a vacancy of 1 electron. So that can act as a hole. So when you adding each group 13 atom to complete the bonding with group 14 atoms, these group 13 atoms absorb 1 electron from neighboring silicon or germanium atom. The group 13 atoms satisfy all the 4 bonds with silicon atoms, but that create a hole in the neighboring silicon atoms. Since the group 13 atom accept 1 electron from silicon, is called acceptor ion or acceptor impurity. Since you are accepting electrons, their energy level will be very close to the valence band. Here, since donating the electrons to the conduction band, the energy is very close to the conduction band energy levels. So here only 1 electron, that is due to the thermal excitation from valence band to conduction band of group 14. But there are so many holes. All these holes are due to absorption of electrons from valence band of group 14 into the group 13 atom. The group 13 atoms demand 1 electron for completing the bond formation. So these atoms accept 1 electron from the valence band of silicon. So out of this 2, 4, 6, 8 holes, 7 holes are formed due to electrons lost from valence band into the group 13 atom for completing the bond formation. Only 1 electron is excited to the conduction band. So here holes concentration, hole concentration is greater than the free electron concentration. So Ne will be less than NH. In all the 3 cases, intrinsic, extrinsic, N-type or P-type, Ne into NH will be equal to Ni square. Ne and NH are after doping. Ni is the electron or hole concentration before doping. So these are the important energy band diagrams related to semiconductors chapter. It's asked as normally 1 more questions or 2 more questions with an explanation additional how N-type is formed, P-type is formed, like that. Thank you for listening.